Hello Leetcoders. So today we are going to solve day 18 problem in the July Leetcode challenge, and the problem is titled as course schedule 2. So this is a variation of a simple problem in which we will have to tell if we can complete a course schedule or not. So in this particular problem we are given n courses labeled from 0 to n minus 1. Some courses may have prerequisite. For example, take take course 0, you have to first take course 1, which expressed as pair 0, 1. So this means like if I have a pair 0, comma 1, it will be expressed as 0 is dependent on 1. So you first have to complete 1 in order to complete 2. So basically it will become like this. So this will become like this. So 0 is dependent on 1. So that is how it will be done. So given a total courses and list of pairs, prerequisite pair, you need to find the orders of the in which the course can be completed. So in this example, we are given two courses 0 and 1, and one course 1 is dependent on 0. So you first have to complete course 0, and then only you can complete course 1. So the output is expressed as 0, 1. Similarly, let's go to the second example. So we are given four courses, and one is depend on 0, two depend on 0, three depend on 1, and three depend on 2. So if we try to draw the dependency diagram here, it will become something like this. So we have course 1, which is depending on 0. Course 1 is depending on 0, and then course 2 also depend on 0. So you basically have in degree of this. So one depend on 0, two depend on 0, and three depend on 1, and three also depend on 2. So if you look at this, you first need to complete course 0 because it actually do not have any dependency. After completing course 0, only you can go to course 1 or course 2. Now after you have completed course 1 or course 2, then only you can take course 3, which is the last course, and you can complete this course schedule as 0, 1, 2, or 3. Or you can do it like 0, 2, 1, and 3. So this would be the kind of output for this. So to solve this problem, the most efficient approach would be to use Khan's topological sort. So I will first tell you the algorithm, and then I will express how we are going to implement this in the given problem. So according to the Khan's topological sort, we make a graph of nodes. So let's just see. Let's let's have a kind of, let's say we have a course schedule which is like this: 1, 2, and then 3. Actually this should start from 0, so let's say there is 0 here. 1 depend on 0, and 2 and 3 depend on 1, and then let's say there is another course here which is 4, and then there's a 5. So according to the Khan's topological sort, this is a graph that we have, and this is a directed graph. As you can see, all the edges are in some direction, right? So if I make a prerequisite of this, so 1 depend on 0, and then 2 depend on 1, and 3 depend on 1, and 4 depend on 2, and 4 depend on 3, and 3 depend on 4, right? So this will be the prerequisite uh, list that we will be provided for this example. According to the Khan's topological sort, we first need to find the integrity of each of the node. What does integrity means? Integrity means how many nodes need to be completed before you can complete that particular node. So for example, in case of one node, we only need to complete 0. So 1 has a integrity of 1. So 1 has integrity of 1. Now, and for 0, we don't need to complete any of the node. So we can start with 0. So the integrity of 0 node is 0. Now integrity of 2 node, which is not this, which is this node. So integrity of node number 2 will be 1, because there is only edge that is coming to 2. Similarly, for 3, the integrity will be 1. For 4, integrity would be 2, because there are 2 edges that are coming on 4, and the integrity of 5 would be 1. So this will be the integrity. Now what we are going to do is we are going to first traverse the nodes which have 0 dependency, which means 0 integrity. So in this case, node number 0 has no dependencies. So we can start from that node. So we start from that node, and our graph will be something like, uh, after 0 you can complete 1, after 2, okay, after 1 you can complete 2 and 3, after 2 you can complete 4, after 3 you can complete 4, after 4 you can complete 5. So this will be kind of a graph that we will be having in. So this is a format of adjacency list. So we will represent the graph like this, where graph is represented as a key value pair, where key is the node and value is the neighbors, list of neighbors. So in this case, 0 has a neighbor 1, 1 has a neighbor 2 and 3, like this. So now after we start with the node which has 0 integrity. After we have completed that node or that course here, we will we will see the neighbors. So now if we look at the neighbors of 0, the neighbors of 0 is 1. Now we go to 1, and we will see how many integrity does 1 has. So integrity of 1 is 1. So if we traverse this, we can decrement this integrity count. So integrity count will become 0. So integrity of 1 will become 0. As soon as the integrity of 1 will become 0, that means we can cover this course now, because we have already completed the prerequisites. So we will put this in the output list. So our output will be like, first, of course, we'll start with the node which has zero dependency, which is node 0 here. And then the so whenever the integrity of any neighbor becomes 0, we will put that neighbor into our queue. So we are essentially doing a breadth first search approach here. And by doing the breadth first search approach, we are starting with the nodes which has zero dependency, and then we are decrementing the dependencies of each of the nodes. And as soon as the dependencies of any of the node will become 0, we put that node onto the queue for the processing. And queue will keep popping the nodes, and that will be the sequence of the courses. So in this case, it, the integrity of 1 will become 0, so 1 will be the output. 1 will come in the output. Then now we will check what are the neighbors of 1. The neighbors of 1 are 2 and 3. Now we decrement the integrity count of 2 and 3. So if we decrement the integrity count of 2, which is right now 1, it will become 0. So integrity of 2 will become 0, and integrity of 3 will also become 0. As soon as the integrity of any node will become 0, we will put that onto the queue. So queue dot append that particular node or that particular neighbor, right? Whole dictionary of list. So this is my adjacency list. So, and I also need a in degree, which will be kind of a dependency. So I'm taking a list here with all geo. Now for each of the prerequisite will be like course, comma, prerequisite. In prerequisite, we will be having, we will populate our graph. Our graph will become like prerequisite dot append course. So first you need to complete that prerequisite, then only you can complete that course. So this will be in sync with the approach that we just discussed. So we first need to complete the prerequisite, then only we will go to the courses, and we need to populate the in degree of that prerequisite. Actually course, because course has some dependency. So this will become +1. Now uh, we will start with the nodes which have zero dependency. So let's say we have a queue, and that queue will having kind of a so let's say I for I in range call num degree if in degree of I is equal to 0, which means we are populating the queue with the courses which has no dependencies. Right now we will start our BFS. we will also need an output list to store the sequence of the courses. Now, let's say we have our current node, whatever we are popping from the queue, and now we will put that into our output list because that that is the proper sequence of the course. Now, for each of the neighbors of this course, so after this course has been completed, we will want to cover the next courses which we can now cover. So next courses we can find uh, from the graph. So now for each of the neighbor we will decrement the integer count, and if our integer will become 0 of that particular neighbor, we will put that onto the queue, which means that now that course has completed all the dependency and that course can now be uh, marked as completed or done. So move you can now do that course because you have covered all the dependencies. So you will put that onto your queue, and at the end you will return out if you have all the courses, length of out equal to num courses. So if you have all the courses covered, otherwise there is a cyclic dependency that exists and we will return empty list. So let me just check this code once. So we have in degree of range, and then for each courses we are appending graph prerequisite into course, and then we are incrementing the in degree of that course by 1. Now we are populating the queue with the nodes which has 0 dependencies. Now we start the traversal of the queue, and after we have the neighbors, we will decrement the integer of the neighbors. If the integer of the neighbors will become 0, we will append to the queue. Uh, so this is working for this example. Let's just try it with another example that we have provided, which is slightly better and cover the case. So this is working for this as well. Let's just submit this solution. This got accepted, and yeah, so I think we are using some space here, so we are making a graph which will take a space of, I think, v into u. So space will be, I think, big O of v plus edge. Edge plus vertex will be the time complexity of the BFS. And I think for space we are storing number of courses at least, so it's going to be n at least, or I would say e of edges or of vertex will be the space complexity, I guess, the most case. So anyway, if you like this video, please don't forget to subscribe the channel and we'll see you in the next video.